Hey everybody, Dr. Retzek here with you. This is our second video in section 16.2. It's a continuation of our discussion of line integrals of vector fields. Let's get started. Okay, so we're in 16.2 and this video is short and is more of a heads up than it is any kind of new content. And so the heads up is about three specific things. So here's the first thing. First thing is a notational thing. We mentioned it in class yesterday, and we'll do it again here. In 16.1, we saw this notation. Line integral of some function, say of 3 variables, with respect to arc length. And you guys recognized that little arc length bit, the ds, as a little bit of length along the curve comes from Pythagorean theorem. It's just the sum of the squares of the derivatives with respect to whatever parameter, all square rooted, all done d parameter. So that was representative of that little bit of arc length along the curve back in 16.1. Here in 16.2, they're asking us to reconsider a line integral of a scalar function, so not a vector field, but this time not with respect to ds. So they want us to consider this. Now, instead of little f, they all of a sudden decide to use capital N. That's fine. It's just a scalar function. There's no arrow over that capital M. This isn't a vector field in any sense. Only this time, it looks a little strange relative to our thinking back in 16.1, because instead of ds, they write dx. And the dx here, basically you're saying, we don't care about the other letters, y and z. We only care about tiny changes in the x coordinate. And so that dx goes into your integral as just x prime of t dt, as if these two just weren't even there. Okay, and if you're willing to go that far, then maybe you're willing to go a little further. And think about the line integral over a curve C of a scalar function capital N with respect to y, which I'm sure you can guess just goes in as a y prime of t dt in your integral. Everything else the same, just like it was in 16.1. Or for that matter, we could do everything dz, where the dz goes in as z prime of t dt. And you sometimes see these three integrals all together in a single problem. And so sometimes people even write this. M of xyz dx plus n of xyz dy plus p of xyz dz. And that just means three separate integrals. Do these three and add them together. It's just super shorthand for that idea. Anyway, if you see any line integrals ending in dx, dy, or dz instead of ds, you know what they mean. Okay, so that's thing number one. That's heads up number one. Number two, this we also mentioned in class. Heads up number two is when you have a vector field, so just a bunch of arrows pointing however, just populating the space where you're doing your math, different lengths, different directions, just sort of scattered about. And you're interested, so that's the vector field big F. Note the arrow over the capital letter. That means at each point, X, Y, Z in space, say, if this is 3D, there is a vector with its tail at that location. And then you're interested in assessing this vector field over some curve, like maybe that's your curve. So it ends there at t equals b, and it began over here at t equals a, and it's being traced out in this direction. And you're interested in the contributions of those black arrows to movement along the curve. So our thoughts were like this. Say you were at this spot on the curve, and that was the arrow. We're interested in the component of that arrow along the curve. We don't care about the part of that arrow for the purposes of this discussion perpendicular to the curve. We only care about the part along the curve in orange. Now, the second heads up is that the line integral over that curve C, f dot dr, that line integral can actually mean something when the black arrows are force. When the black arrows are force, then that component of the black arrow in the direction of the curve, so the orange piece, that's a force in the direction of motion. And you're multiplying that by that tiny little length ds, and so that's a tiny little bit of force times distance. So that's a tiny little bit of work, and then you're adding up all those little tiny bits of work over the length of the curve. So this is total work. When your vector field is actual forces. So it's work whenever the black arrows represent force, because these little ingredients right here amount to little bits of force times distance. So if you see any problems that say compute the work for the vector force field, blah, 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 they just mean do the line integral like you've been doing, but you can actually recognize it as having some sort of physical meaning. And if the forces are given in newtons and you're thinking of distance in meters, then you have Newton meters, you have joules. Or if it's feet and pounds, you have foot pounds. In any case, when the vector field is a force field, you're really just calculating work. Okay, third heads up. Third heads up. There is one particularly useful and ubiquitous type of vector field that will be important to us moving forward in chapter 16. Suppose f is a function from 3D space into the reals. So this is like a classic chapter 14, chapter 15 kind of function, f of x, y, z. Then the domain of that function is 3D space. And we can't even see the graph of it because I'm no good drawing in 4 dimensions. So what you're looking at there is just domain space. There is a way to populate the domain space with a bunch of black arrows at each point that is born from the function f itself. So say you're at the point x, y, z in 3D space, and you're looking to place a black arrow with its tail at that dot. The black arrow could be the gradient of the function f. So that's gradient of f specifically at that location. And you guys remember the gradient is df dx there, comma, df dy there, comma, df dz there. And the gradient points, just like you already know from chapter 14, the gradient points in the direction of greatest rate of increase of the function f. So if you were a fly hovering right there at xyz, and f represented what? I'm trying to think of something like something the fly would want. Food? I don't know. But if you were hovering right there and you took off in the direction of the gradient, you would be flying exactly in the direction of greatest rate of increase for f. That's the direction you should go to make f bigger as quickly as possible. And if you're trying to get away from something, like maybe a predator or something like that, and you're hovering at xyz, okay, well, go exactly opposite the gradient if you're trying to get away from something like, oh, like a bug zapper or something. Maybe the opposite of the gradient is the direction of greatest rate of decrease in danger or whatever. And you can do this at every single spot. So depending on where you are, these gradients will be different lengths and point in different directions. But truly, at every spot, you can write down the gradient. And in that way, you can populate 3D space with a bunch of vectors. And this is called the gradient vector field. So if you see any problems that say, find the gradient vector field for blah, 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 all they mean is they're going to hand you some function. You write down its gradient, and you have written down a vector field because at each point, you have some vector. Anyway, it's mostly terminology. It's nothing new idea-wise beyond the introduction to 16.2, but it is a few new ideas notationally or terminologically that we want to have ready to go moving forward. Anyway, try some of those suggested problems and come to class with questions. I'll see you soon. Bye.